All right, today is Monday, January the 11th. We're in advanced level chemistry. And today is going to be a day to where we go through and we start looking at why or how do atoms actually bond together? What are the mechanics of how they bond together? And so we're going to be talking about this thing called hybridization. And on the fill-in notes, we're going to be starting on page 2, letter F is where we're going to be. And if you notice, there's not a whole lot to fill in on this. But when we look at hybridization, if I take a red rose and a white rose and I hybridize, what do you expect to get? A pink rose, right? Something in between. You hybridize, you're going to get a mixture of the two. You could get a red polka dot rose. Now, just out of curiosity, if I say a red polka dot rose, okay, what do you see in your brain? A red rose with white polka dots or a white rose with red polka dots?
I think a red with white dots.
Red with white dots? What about y'all? Is that what y'all kind of see? See, but it's a red polka dot, so some people see the red dots and a white rose. So anyway, it's just kind of, I always kind of think about that on what do you see, whatever, but it has absolutely nothing to do with this. So, hybridization. What is the definition of an orbital? The possibility, the probable place where you're going to find an electron, okay? So we have an orbital for an atom. We learned about the s orbitals being spherically shaped, the p orbitals being dumbbell shaped, and all the different shaped orbitals. And that's the way they are when they're an atom, okay? But when they go to combine orbitals, the electron orbitals are based on energy. They're energy sublevels. So when the energy changes, where the electron's going to hang out changes. So all hybridization is if we take an s orbital, which is spherical, and combine it with a p orbital, we're going to get the hybrid orbital is going to be a fat and then just a little bit there. This is your hybrid orbital. So when we're talking about hybridization, all we're saying is that the electron, when the atoms start coming together and they want to bond, the electrons change where they hang out, and instead of being in this shape or in this place, they're going to be now in an area more like this. They're going to hybridize. Okay? Now, how do we know this occurs? Why does this occur? If I look at, I'm going to just stay right here. If I look at carbon, okay, 1s, 2s, 2p. Carbon has 6 electrons. It's going to look like that. Okay? If I was to draw the Lewis dot structure for carbon, and this is carbon, really I need the valence electrons, got 4 of them. I would need 2 paired up in the s and then 1 like that and 1 like that. So when it went to bond, you only have 2 unpaired electrons. Hydrogen would come in here and bond. Hydrogen would come in here and bond. But we get CH2 as our molecule. Well, CH2 doesn't exist. What's the problem with carbon here? It only has 6. It doesn't have. It needs 4 paired instead of just the 3. So scientists have to try to figure out, well, how can carbon? Because we know carbon forms CH4. So this is what we call the ground state, the lowest energy state. But carbon, they said, well, maybe it goes to an excited state where this electron jumps up from the s into the p. Okay? So the electron is here, 1s, 2s, 2p. So one jumps up into here. So now I have 4 unpaired electrons. But the reality is that 3 of them would be a p, and so the p orbitals are going to look like this, like this, like this. You'd have 1 electron into each of these, okay? 1 electron into each, but somehow or other we try and have to put a s orbital in there with a, okay? Now, when the hydrogen comes in to kind of bond, it's very difficult to get in to overlap here, because we have to overlap on our electrons. So that doesn't quite work. Plus, 3 bonds would be identical, 1 would be slightly different. All 4 bonds are exactly the same here. So this is where the concept of hybridization comes in. So what scientists have figured out is that the electrons, these all just kind of rearrange, they hybridize to where we no longer have an s and a p, we get 4 equivalent orbitals, and they're going to be more energetic than an s, less energetic than a p, and we're going to get 4 hybrid sp3 hybrid orbitals. 1 electron into each. So now we have 4 equivalent orbitals. Those 4 things, electrons, and I'm going to kind of do hand in hand here today. You guys all look so energetic, so fired up to be here today. All right, so we're going to be taking and looking at the hybridization and also a theory called the valence shell electron pair repulsion theory. The valence shell electrons are going to repel one another and get the maximum distance apart. So these 4 electrons, what that means, these 4 electrons are going to get as far apart from each other as possible. Now I'm drawing this, so this is my sp3, 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 sp3. So now the hydrogen can come in here with its s orbital and bond, another hydrogen with its s orbital and bond, and we get 4 equivalent sigma bonds making CH4. That's kind of what goes in the blank on your fill-in notes. Okay? So, when we look at this, those 4 orbitals, now I drew this in 2 dimensions, but it really exists in 3 dimensions. So when I go and I look at that, it's going to look like this. Each of the reds, I don't know, kind of a globe, sphere, whatever, these red orbitals, these are your hybrid orbitals. Notice that they're all pushed away as far as we can. There's 4 faces on this, so we call this a tetrahedron. Okay? So the electrons are arranged in the shape of a tetrahedron. The bond angle is 109.5 degrees at all points right here. So they're all equally pushed apart. The valence shell electron pairs are going to repel one another to get the maximum distance apart. So when you have 4 things that hate each other, this is the way they can arrange themselves to be the maximum distance apart in the shape of a tetrahedron. We call this sp3 hybridization because the s orbital and all 3 of the p orbitals changed. 4 orbitals to start with, 4 orbitals to end with. Law of conservation of orbitals. Orbitals are neither created nor destroyed, they just hybridize. Okay? It's not really a law, but it sounds good. So, sp3, all 3 of the p orbitals hybridize, so it's sp3, so we get 4 equivalent hybrid orbitals. Now, this doesn't just happen with carbon. Generally, anything that has 4 electron pair domains around it, 4 pair of electrons around an atom, in other words, a filled octet, anytime you do that, you're going to get hybridization. Let's look at nitrogen. If we want to figure out how ammonia is going to form, okay? Now you might want to just do this on the back of a sheet or whatever because there's no space in your notes for this. But if I look at nitrogen, Nitrogen, oh, by the way, this is called the excited state. And this is called the hybrid state. Okay? So if I look at nitrogen, nitrogen has how many electrons?
Total?
Total.
7.
5 valence, 7 total. 1, 2, 3, 4, 5, 6, 7. Now it seems like with this one, NH3 is easy because we're going to draw the Lewis dot structure looking like this. Seems like again the hydrogen could come in here, hydrogen could come in here, hydrogen come in here. But again, these are your p orbitals. Who remembers how are the p orbitals oriented to one another? What's the angle? How are the 3 p orbitals oriented?
Perpendicular.
Perpendicular to each other, on the x, the y, and the z axis. So what's the angle on perpendicular? 90 degrees. So if we looked at ammonia, and if this is the way it bonded, just with the p orbitals, all the bond angles would be 90. And guess what? They're not. Okay? So possibly it goes through the excited state, just like this, promotes one up. But then again, we have the 2 90 degrees and then this S. That doesn't make any sense. So it goes and hybridizes. And this time, we put a nitrogen here. But one of these is just going to be a lone pair. The electrons are still occupying 4 different places around the central atom. It's still sp3 hybridization. But the bond angle, here it's 109.5. That's standard for a tetrahedron. And I'll come back and explain these a little bit more. But with NH3, it's 107.3 degrees. How can that be? Well, when you have nitrogen like this, nitrogen here, a hydrogen here, now again, notice this is the same shape as this one, okay? It's the tetrahedron, the 4 faces, okay? But now this is a lone pair, so we can represent that. Okay, so that's a lone pair of electrons up here. So now when we look at this, there's still points of a tetrahedron, but lone pair occupy a greater space than bonding pair. There's more electron-electron repulsions. These things are worth writing down. There's more electron-electron repulsions. And so as a result, we say the shape of the molecule is pyramidal, but this lone pair up here occupies a greater space because there's no positive up here. You have a positive here, you got a positive here, help balancing out the negatives of the electrons. But when you have a lone pair, they occupy a greater space. So they're going to kind of like close the umbrella a little bit. They're going to make these atoms a little bit smaller by about 2 to 3 degrees per lone pair. So we're still a tetrahedron, okay, as far as the electrons. We say the shape of the molecule now is trigonal pyramidal, but the bond angle is about 2 degrees less because of the lone pair. Do one more of this one. Oxygen. How many electrons does oxygen have?
6, 8.
8 total. 2, 4, 5, 6, 7, 8. Okay? So now, again, when it goes to hybridize, the excited state here, now we're going to do the exact same thing. Oxygen is going to be here. This is going to now be another lone pair, and then we have the 2 hydrogens. Water is a bent molecule because it's got 4 pair of electrons, so they're going to arrange themselves at the points of a tetrahedron, but 2 of them are going to be lone pair, okay? So we don't count that. So, but these can't come up and be linear because of the presence of these electrons repelling and pushing them down, because negative repels negative. Okay? So water ends up being bent. If water wasn't bent, if water was linear, it would be a gas at room temperature. Life as we know it would not exist on Earth if water were linear instead of being bent. Those two lone pair are very important. What do you think the bond angle is approximately in water?
120.
No?
105.
Somewhere around 105. Because it's going to be 2 degrees per lone pair decreased. So we're going to start at 109.5, but for water, with 2 lone pair, the actual bond angle is 104.5, I believe. My brain's going. Okay? 104.5 degrees. Because the 2 lone pair. But it's sp3 hybridization. Anytime you have 4 pair of electrons around the central atom, they're either all bonding or lone pairs. There's no double or triple bonds. It's going to be this sp3 hybridization. All right. Just ponder that thought right there. Okay? This is how atoms rearrange. This is how they're going to bond. This is going to determine their shape, and their shape's going to determine all their properties. Okay? So let's come back to carbon now. So by the way, we can go on here, we're going to say the shape is pyramidal, and here the shape is bent. Okay, so the electrons are all arranged in the shape of a tetrahedron, but the shape of the molecules are given based upon just the electrons that are there. All right. What if, though, we want to make a double bond? We have C2H4. That's going to look like this. What are my sigma bonds? What are my pi bonds here?
All of them are sigma except for the carbon to carbon.
Okay, so we're going to have sigma, 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 sigma. What about both of these pi?
No, the second one's pi.
The first one's sigma, the second one is a pi bond. Now, if you recall from Friday, only p orbitals can form pi bonds. Hybrid orbitals cannot form a pi bond. S, D, F, none of them can. Only p orbitals can form a pi bond. So somehow, some way, when this carbon, and both carbons are doing the exact same thing, when each carbon is in this ground state, it goes to the excited state. When it goes to hybridize, it knows, hey, I gotta form a double bond. So I can't have all 3 of my p orbitals hybridizing, because the hybrid orbital can't form a pi bond. So this time we're going to only take an S and 2 of the p's, and we're going to end up having 1 2p orbital left over with 1 electron in it. So what type of hybridization do you think this is going to be called? The first one was sp3 because the S in all 3 of the p's. What's this one going to do?
SP2.
sp2. Because only 2 of the p orbitals are involved in hybridization. So this is sp2 hybridization. So now these are what's going to determine the shape. 3 things that hate each other. I'm going to go here, here, and here. These are my sp2s. And the other carbon is doing the exact same thing. So here's my sigma bond between the 2 sp2s. I bring a hydrogen in here for a sigma bond, a hydrogen in here for a sigma bond, a hydrogen here for a sigma bond, hydrogen here for a sigma bond. So those are all my sigmas. But now I need a pi bond. Well, the three things that hate each other to get maximum distance is going to be 120 degrees, is going to be a triangle. So this is a flat molecule. So on this, but perpendicular is going to be the non-hybridized p orbital. If you remember, a pi bond is the side-to-side overlap. So these are going to overlap here and here to make my pi bond. This is sigma, 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 sigma. But my pi bond is going to be the p orbital. Now that's again drawn in 2 dimensions. This molecule is decomposing rapidly. Ugh. See if I can get it back together. Okay, that's the start. So what we have, this is the exact same thing as I just tried to draw, but now you can see it in 3 dimensions. Okay? Each of the red are your hybrid orbitals. So each carbon has 3 hybrid orbitals. They're going to arrange themselves 120 degrees apart in a flat triangle. That's the way 3 things that hate each other can get the maximum distance apart. The valence shell electron pair repulsion theory. The electron pairs are going to repel one another. Get as far apart from each other as possible. The green are your pi bonds, perpendicular to the plane. But only p orbitals can form pi bonds. So as a result, we have sp2 hybridization. Anytime you have a double bond, you cannot have sp3. It's either going to be sp2 or the next one. All right. None of y'all, I don't see any of y'all drawing these on your paper, but hopefully you'll go back and study this video, trying to figure out what the heck's going on. But the reality is once we figure this out, to be able to tell SP, SP2, SP3 hybridization is really fairly simple, the actual process itself. All right, finally, we have a compound, C2H2, acetylene. And in acetylene, the formula is here. So now what do I have? I have a sigma, and a sigma, and these two are both, the second and third are both
Pi bonds.
pi bonds, okay? Pi, pi. So I have 2 pi bonds. So how many p orbitals do I have to leave unchanged? How many p orbitals? 2, because I need 2 pi bonds. Only p orbitals can form pi bonds. Therefore, I need 2 unchanged. So I go with my normal ground state. I go to the excited state. But this time, I need to leave 2, so only the S and one of the p's hybridize. And I'm left with 2 non-hybridized p orbitals. So what type of hybridization are we going to call this? How many of the p orbitals are involved? It's just going to be sp. Because it's the s and a p, and then you leave 2 p orbitals. Notice you always have 4 orbitals. It's just, are they hybrid or are they regular? So, 2 things that hate each other. How are they going to arrange themselves at 2 things that hate each other? Not perpendicular. Parallel. They're going to try and be opposite, right? And so, if I take a carbon, it's got this sp, sp, another carbon, sp, sp. This is my sp, sp, sp. Okay, I need to be doing these in Carolina blue because it's Spain Park orbitals, sp. We're actually, our AP chemistry t-shirt is going to be we are SP, and it's gonna have all the molecules that have SP hybridization. In their good nerdy AP chemistry t-shirt. Okay, so the hydrogen can come in here and form the sigma bond. The hydrogen can come in here and form the sigma bond. So those are my hybrid orbitals. Each carbon has 2 of them. Okay, but each carbon also has 2 p orbitals that are non-hybridized. So those are going to, this is the x-axis. The p orbitals then are going to be on the y and the z. So you're going to get a p orbital above. And so they're going to overlap here. Then we're also going to get, I don't have any other colors, p orbital in and out of the board. They're going to overlap in front and behind. Now that drawing is very difficult to see. But this kind of shows you really what it's going to look like. Your carbon's in the center here. This is your hybrid orbitals. This is a sigma bond between the 2 carbons right here. Here's the sigma bond with the hydrogens on the end. So it's a linear molecule. It's straight on the x-axis, but then you have p orbitals, the green unchanged. So this is the pi bond above and below. Now it's overlapping in 2 places, but that's 1 bond. This is not 2 pi bonds. So this is the second pi bond out in front and behind. Okay, so we get all of these different shapes based upon how the molecules bond. So if you have sp hybridization, it's always going to be a linear molecule. This is sp2, this is sp3. The electrons, the hybrid orbitals determine the real bonds because they're going to form the sigma, the first bonds. They're going to determine the shape of the molecule. Okay? So, it's really quite easy though. Turn the camera just a hair over this way. If I give you this kind of crazy this crazy compound right here. And I'm going to ask you, what type of hybridization is taking place on each carbon atom in here? Okay? Well, I know that if it has 4 bonds, so I'm going to look at this carbon right here, and I'm going to say it's a general formula. A is the central atom, and it's got 4 things bonded to it. 1, 2, 3, 4. So I'm going to say it's AX4. A is the carbon, each X represents the hydrogen, and the other carbon. 4 things attached to it. Well, that means I have 4 orbitals, 4 places where the electrons are hanging out. So this hybridization means I have to add up to 4. So SP, SP2, or SP3 adds up to 4. SP is 1 and 1, so that adds up to 2. If you need your calculator, we can do the calculator. Okay? SP2 is 1 plus 2 equals 3. So SP3 is 1 plus 3 equals 4. So this is going to be SP3 hybridization. So I know around this carbon it's going to be SP3. But if I look at both of these carbons, this carbon is bonded to how many other things? Well, 1, 2, 3. Yes, it's a double bond, but there's still just 3 things attached to this carbon. So I'm going to say that that's AX3. Okay, don't worry about the double bond. I just have 3 things attached to it. AX3. So what adds up to 3? Which type of hybridization?
SP2.
SP2. Okay, now if I look at these 2 carbons, how many things are attached to each of those 2?
2.
2 things, 1, 2. Okay, so we're gonna say it's AX2, so what type of hybridization is it?
SP.
SP. So what do you think this one's gonna be?
SP2.
SP2, and this one's gonna be
SP3.
SP3. Which means the shape around the SP3 is gonna be something like this. You're gonna see it's gonna be tetrahedron, the four points making the four faces. This is the top of the tetrahedron right here, okay? That's your CH3. When we have double bonds, okay? When there are double bonds like this one, then the shape is always going to be trigonal planar. So you see here, here's your triangle, okay? 120-degree bond angles. Triple bonds are always going to be linear. So based upon the type of hybridization, so I can look, it's very simple. So if I have a molecule SO3 that looks like that, what's my AX formula gonna be of that?
AX2. I mean, I'm sorry, AX3.
It's AX3, so what type of hybridization is it?
SP2.
SP2. Okay? Even in AP chemistry, all you have to be able to do is identify. You don't ever have to go through this explanation. I just didn't want to just teach you this without having some kind of background of why or how it does it. Okay? It's just in order the atoms rearrange in order to accommodate bonding better. They rearrange so that the atoms don't get in the way of each other. They're all repelling to try and get as far apart from each other as possible. Okay? So HCN, okay, and we're just going to look at the central atom. What's the AX formula for carbon here?
AX2.
AX2. So what type of hybridization is that?
SP.
SP. Y'all seeing that? Okay, so really the hybridization is complicated in, as far as trying to understand all this, but their actual practical application is pretty simple based upon the Lewis dot structure. Now again, I've told you, knowing how to do the Lewis dot structure is the ultimate and most important thing, because everything that we're going to do is based upon that Lewis dot structure. Now, we want to know the shapes of different molecules. So knowing that atoms hybridize, knowing that if there's 4 things around the central atom, it's going to be sp3. If there's 3 things, it's sp2, and if there's 2 things, it's sp. We can then determine the shapes of our molecules based upon these AX formulas and how the electrons are going to repel and get the maximum distance apart. I'm going to post this online for you guys, so you'll have a copy for yourself. But we're going to start, we'll start right here. Okay, the different types of hybridization and the different shapes of our molecules. So again, if we start with a molecule that has 4 equivalent bonds, we know that the shape is going to be tetrahedron. Anything that has 4 things around it is going to be a tetrahedron. It's going to be AX4. But we could have ammonia. Where's that model? What did I do with that one? What did I do with the one molecule that was right up here I was just using? I hate it when I set stuff down, I can't find it. Okay, if I take one off and I have a lone pair, now this is going to be, when I look at like ammonia, this is CH4, would be an example of this. sp3 here would be ammonia, nitrogen, hydrogen, hydrogen, hydrogen with a lone pair. So A is always the central atom. X is the number of atoms that attach to it. E represents lone pair electrons. Okay, so there's one lone pair electron, so it's AX3E. But 3 plus 1 still adds up to 4. And then water looks like, and there's my molecule. I think the other one's over here. Okay, water has 2 lone pair. And so the oxygen in the center, but the lone pair is still at the points of a tetrahedron. Okay, but we say the shape is bent. We say that this is AX2E2. But 2 plus 2 still adds up to 4, so it's going to be sp3 hybridization. Notice the bond angles decrease by about 2 degrees every time. Now, you're not going to need to know exact angles because it's always going to be different, but it's going to be about 2 to 3 degrees per lone pair. Okay? Now, when I look at trigonal, this one, at AX3, now we're going to start having double bonds. This would be sulfur trioxide. And when we're looking at lone pair, that E that's only on the central atom. It's not on the peripheral atoms when we're looking at our general formula. It's only on the central atom. So, this has got AX3, so it's going to be trigonal planar. If we were to draw that, yes, O, seriously, if we build this one, it's going to look like this. Notice it's totally flat. It's a triangle. Trigonal planar is the shape. What's this bond angle going to be? An interior bond angle on a triangle. 120, because it all adds up to 360 going all the way around. So 120, 120, 120. You learn geometry so you can apply it to a real situation like this. Okay? 120, 120, 120. Trigonal planar. But what if one of them's a lone pair? Now the shape, we're simply going to say, is bent. Bond angle, it's going to decrease some, probably not quite as much because there's already more space, 120 degrees versus 109. Okay? But it's still going to decrease it slightly because lone pair occupy greater space. So we say the shape is bent. If it's anything that has this general formula, and this would be SO2, which would look like this, with a lone pair. Okay? That's going to be AX2E. So we're just going to call it bent or angular. And then anything that's just two things, anytime you have a triple bond, I gave you the example of HCN. We could also look at carbon dioxide. Notice that carbon dioxide is just AX2, no lone pair on there, so it's sp hybridization. That makes it linear. CO2 is a gas at room temperature because it's linear. If CO2 were bent, CO2 would be a solid or a liquid at room temperature. But so the shape determines a lot about its properties. That's next week's, or actually the end of this week's discussion. Okay? So, these other ones involve expanded octets. Now with expanded octets, we don't have to worry about hybridization. It's more complicated. They used to think d orbitals were involved in the hybridization and they had sp3d, sp3d2 hybridization, but research in the past 10 years has shown that d orbitals are not involved in hybridization, and so therefore We don't even include, we don't worry about hybridization for expanded octets, the one that have more than 8. We just need to know the general formula and the shape. So, 5 things that hate each other. 5 things that hate each other. One, two, 3, 4, 5. Okay? 5 things that hate each other are going to arrange themselves like this. Okay? This is called a trigonal because it's a triangular base, bipyramidal because there's 2 pyramids, one on top, one on bottom. Trigonal, bipyramidal. Now the bond angle in here is 120 degrees, but this bond angle is 90 degrees. Now, one of them's a lone pair. So now we go with the shape of the molecule. Now notice the electrons are still in trigonal bipyramidal. Well, one's a lone pair, so now when we say the shape, this really isn't any shape at all. Okay? So they made one up, and they call it a distorted tetrahedron. But then somebody must have just had a kid or something out on the playground. They said, ooh, it kind of looks like a seesaw. I see you, I saw you, I see you, I saw you. It looks like a teeter-totter. You call them teeter-totters or seesaws? Seesaw, right? There's no longer on playgrounds because this kid would always jump off, you know. This kid would jump off and then this kid would go smashing down and break his butt, you know. So I don't think they let them. They're too dangerous now for modern day children. Okay, on the teeter-totter. But so seesaw is a legitimate name though. Now, when we do the lone pair on this trigonal bipyramidal, it always comes out, this is called the equatorial position, like the equator around the Earth. 120 degrees versus 90 degrees. Electrons want to get as far apart from each other as possible, so they're going to stay in the 120 area. So now the second lone pair is always going to be here. Now we just have very creative name, T-shape. T-shape. If we have 3 lone pair, now it's a linear molecule. So all you have to do is know your AX formula. So we only have a few minutes left, but get that Lewis dot structure worksheet out that we did 1 through 6 on. One of those up here. Okay? So, if I look at HNO2, we drew this one already. It's going to look like this, O, and the hydrogen, oh, I'm going to do the double bond up there, and the hydrogen there. With a lone pair on the nitrogen. That's your Lewis dot structure, right? So I want to say, okay, on this nitrogen right here, what's my AX formula going to be? AX2E, because of that lone pair. 2 plus 1 adds up to 3. So what type of hybridization is on the nitrogen? sp2. What's the shape going to be around that nitrogen? I took it down. Okay, so if we look here at sp2, ax2e, it's going to be bent. Right? Now you're going to get this sheet. Okay? You're going to have this sheet. Now, you would have the sheet anyway because now that we're staggered like this, all tests and everything are all have to be open book, open note because it's only fair. So but you don't really have to memorize this. We just need to know how to apply it. Okay? Now, let's look at the oxygen right here. What's the AX formula around this oxygen? We don't say the shape of overall molecule. We say the shape around each central atom. So since this has 2 things bonded to it, it too is a central atom. So what's the AX formula around this one?
AX2E2.
AX2E2. So what type of hybridization is it? 2 plus 2 equals 4.
SP3.
SP3 hybridization. And then the shape around this one is going to be bent as well, but just with a different bond angle. So tomorrow in class, while you guys are at home, we're going to go through and we're going to look at and finish drawing the Lewis dot structures and then go through and try to figure out what the shape is and the type of hybridization on all of them. Okay? So that's what you guys are going to need to do at home tomorrow. And you can follow along in the video if you want, but that's what we're going to do. We're going to go through and make sure we know how to draw the Lewis structure for everything, and then use the AX formula to figure out the type of hybridization and the shape of the molecule. Because the shape of the molecule is going to determine the properties. I already kind of alluded to it. Carbon dioxide's a gas because it's linear. Water's a liquid because it's bent. So it's super important on the shape. But it's all based on Lewis dot structure. So we're going to build. So we got to make sure we know each step of the way.